Hello, these slides are to do with AM modulation for ELE 8940 labs. And a really good resource on the internet is this site from Rode and Schwartz. They make equipment for measuring spectrum and so on. And you can click on this link here and get to that. You should watch that video. It's pretty good. Now, in the lab, you're going to be working with a software that's called Jakarta. And you're going to be either controlling it using AM or FM modulation. You should have this little adapter that's going to plug into the headphone jack on your laptop or computer, and you'll be connecting the picoscope to the left channel and ground on this adapter to make measurements. One of the things you'll notice is when you do 50% modulation, okay, this one happens to be 75, but when you do 50, what you'll notice is that the software will actually, when you measure it, it'll be 33 to 35% in the picoscope. Not sure why that's happening. I've contacted the company, but last semester the students encountered this same issue, so be aware of that. Okay, in this slide, here's one of the methods to determine the percent modulation, or the modulation depth, in this case in percent. What I did was set up a generator. So I'm actually using a generator here. I'm going to get the right answers probably. And I noticed that my peak was at minus 2.05 dBm and my side bands were at minus 20.23. So I find out the difference between the sideband and the carrier frequency, and that gives me an answer here of minus 18 dB. Okay, so once I find that, I'll notice that I put that into the equation where it's going to be 10 to the minus 18.2 divided by 20. And we're dividing by 20 because we're trying to determine a voltage difference. And that gives me this value. And then you have to multiply it by 2 for the sidebands. And that gives you 0.246. That's a ratio. That's actually the value of M. But we want to multiply it by 100% so that we can get it in a percent ratio. And so for this particular example, it's 24.6%, which is the modulation index, which is the M. Okay, moving to the next slide. A second method of doing this, and I think this is the same method as shown in the lab, is to take the difference between the peak value and the sidebands. So these are the sidebands, and this is the, this is the sideband, and this is the frequency of the carrier, and the peak is right there. So it's the difference between those two peaks. And you apply it to this formula. The difference in decibels divided by 20, again, because we're trying to get a difference in voltage. That brings you down to this value of 2 divided by 8.1. That works out to be 0.246. And as a percentage, 24.6. So whether I did it this way or this way, I get the same answer. Okay. Now, another way to calculate the modulation index is using the scope. Okay, so using the time domain. And what I need to find out is, looking at the signal on the picoscope, I want to set up one of my cursors so that it's at the minimum value of that modulation point, and then the maximum value. The E represents voltage. And so that really is telling me the difference in the modulation voltage divided by the carrier voltage. And you can determine the value of M by taking E max, subtracting E min, and then dividing that by E max plus E min. Okay. And in this example, these are the values I obtained. 123/49, that gave me 0.25, but to get it in percent, I multiplied by 100 to give me 25% modulation. So in this particular example, I was down minus 26 dB from the carrier. Okay, so the carrier was at minus 13. The sideband was at minus 39.78 dBm. So I have a difference of minus 26 dB from the carrier. So I can calculate it in two different ways. You can say 10 to the minus 26 divided by 20. That gives me 0.05. Multiply it by 2 for the two sidebands, and that gives me an index of 10%. Or you can do it the same way they show in the manual, or in the lab, sorry, where you take 2 divided by 10. Let me highlight this. 2 divided by 10 to the 26, that's the difference. And then divided by 20, and you get 0.1 or 10%. Now notice these four captures here. This just shows you the difference in ratio. So the higher the ratio, or higher the difference in voltage from the carrier to the sidebands, means you're going to have a lower index value. Okay, it's 0.1 or 10%. The closer they get, the higher the index value will be, 0.9 or 90%. So here's another example using the oscilloscope, or the time domain. And I'm just going to point out a few things here. So with respect to the center, 0 volts, the carrier voltage is from here to here. And in my particular case, I had the peak value of the carrier equal to 250 millivolts. Okay, it was 500 millivolts peak to peak. So my carrier works out to be 250 millivolts. Okay. Yeah, the carrier works out to be 250 millivolts, and the peak value of the modulated signal is, I've recorded it somewhere here, about 123 millivolts. Okay, so to calculate the modulating index, I'm basically going to divide the modulation signal by the carrier signal, which in this case is down here. 122 millivolts divided by 248, I get about 0.49, which is 50%. Okay, so that's another way to do it when you have the scope display. And here's just a couple of other examples. I think this is the same, pretty much the same thing, and pretty much the same thing here. So I won't repeat that. And what I did here is created a program, or an Excel file, that allowed me to look at the difference between the carrier frequency and the sideband frequency, and what percent modulation it would produce. So for example, you can see over here that if I had a modulation index of 0.3, which is 30%, I would come over here, and it should give me a value of about minus 16.5 dB, and it does. If I have a modulation index of 60% or 0.6, I'd come over here, and you can see that I should have a difference between the carrier and the sideband equal to about 10.5 dBc, okay, with reference to the carrier. So it's the difference between here and here. And here is actually a third method that you could use. It's not my favorite method, but you could use it. And down at the bottom here is the ratio of the voltage of the sideband compared to the voltage of the carrier. So it's a ratio. And in this particular case, it's measuring the difference in dB from the carrier to the sideband. So for example, if I had a difference of minus 12, which would be right here, okay, minus 12, I'd come up this line until it hits that diagonal. So right up here hits that diagonal. On where it intersects, if I come across from that, this would be 10, 20, 30, 40, 50. So it would be giving me 50% modulation with minus 12 dB. If I had minus 20 dB, let's just see what it would be for minus 20, come up vertically and then across horizontally, and that's 10%, 20%. So let's just check that with the previous page. So I said minus 20 dB would give me 20%. Well, actually, I have it right here. Minus 20 dB, 20%. So that works out. And minus 12 right here gave me 50%. So it's just another way. So you can do it with the calculations that we had on the previous page. You could actually make use of this chart or of this chart. Any of these techniques will work. Okay, and here's just an example where I did it using the voltage. Okay, but you'd have to convert the voltage. And here I've got an example on how to do that. So I use the technique that they have in the lab. So M is equal to 2 divided by 10 to the difference in dB divided by 20. And it works out to be, this case, 14.38 minus 2.154. So a difference of 12.2 dB. Put that into the equation and you get 50%. Okay. Or you can do it, oh yes, the second method I wanted to show you was actually measuring the voltage. So here I have a 50 ohm load, and you set that up in the picoscope. So I'm using a 50 ohm load, and the voltage of the carrier is going to be equal to the power times the resistance, or the square root of power times resistance. So I can figure out the power first. The power is equal to 10 to the 2.154 for that peak value, and then divided by 10 because we're working with power, and that gives me 0.609 milliwatts. And to figure out the voltage of the carrier, it's the square root of 0.609 milliwatts, which is 609 microwatts times 50 ohms, gives me about 175 millivolts. And that's what my signal was equal to. It's actually 500 millivolts peak to peak. But it works out to be 177 millivolts RMS. That's actually RMS. I think I also did it for the minus 14.4 right here, and I figured that voltage to be 43 millivolts. And then I came here. This was just another example of calculating volts RMS given dBm. Okay, I think I went through the whole example here. And this last slide was just doing the same thing, figuring out that peak value with a 50 ohm load resistor. And make sure you know how to do all these RMS calculations. Hopefully this little demo helps you out.